Okay, good to be here. Thanks, Chris, for inviting me and being very patient when I took very long to reply to all your emails. So this talk is designed.
You were aware of that.
Huh?
You were aware that I was chewing my fingernails, waiting for you to reply to my emails.
I was not taking pleasure on it.
I didn't know that I was.
Anyway, so this is a talk that's designed for after lunch, which means that there's no like very big chains of reasoning that you need to follow, and there'll be lots of pictures. So hopefully this will keep you happy. It's about modeling physical agents in quantum, but also in other theories. And this is joint work with Vilasini, that's Vilasini here, and Nuria Nurgalieva. So Vilasini is a PhD student of Roger Kolbach's in New York, and Nuria is a PhD student in Zurich with Renato. And there's two papers. So this paper is Nuria and me, and it's on the archive. And this paper here is Vilasini, Nuria, and me, and it's in preparation, so it will be ready very soon. And that's apparently it's me with amazing hair. And all the pictures, so all the nice pictures were drawn by Nuria. So what's the problem? As your coffee gets entangled with the environment and thermalizes and cools down, I can tell you just a recap of the problem as we see it. And the idea is that, so we want our physical theories to be based on our perceptions, so things that we can go and measure. And they also want us to allow us to reason, to make inferences and predictions, right? It's like minimum requirement for physical theory. But so more precisely, we want them to be consistent with some kind of logical system, okay, which we'll get into, which should be applicable not just for a single agent, but also because I believe in people, to groups of agents that can communicate or make inferences about each other. Okay. But at the same time, we don't want to say that there's something special about us. We also want to model all the agents as physical systems that live in the same universe, and all this information acquiring processes and reasoning processes as physical evolutions. Okay. So this is kind of minimal requirements for physical theory that you want to be, in some sense, universal. And as we saw in this conference ad nauseam, in quantum theory, this can lead to some kind of paradoxes and contradictory situations, right? And our starting point was like, is this unique to quantum theory, or are there other theories in which you can find this, and then what are the features of the theory that would lead to this kind of paradoxes? Okay. So that's the idea. In this talk, so in the first part, I'll set up what we mean by agents, or at least try to say, like, independently of a theory, what we want from something that we call an agent. So in terms of the logic and the reasoning, but also in terms of how we model them as physical systems, and also what's very particular to all of these experiments that we've seen is what a measurement is and how we define a measurement. And then we apply this to quantum theory, which will be very, very familiar and straightforward, and we'll derive such a paradox, which will be just a Farage-Renner one. And then what's new is like try to apply this to a different theory, and in this case it will be a box world. Okay, so whenever there's a picture with a tree, it means that we go to one of these new topics. Okay, so that's my dog trying to climb a tree.
Why is there a squid on the block sphere?
Aha, good question. The answer is at the end. Okay. Okay, so first let's talk about agents and what our desiderata are for physical thinking agents. Okay, so what we want. On one hand, we want to be able to model their reasoning, which means we want to associate them with some kind of abstract operators and some abstract logic system. Okay, and this will be some epistemic model logic, which I'll explain what it is in a bit, and it's already a bit modified to fit physical theory. And it should allow them to make inferences about each other's knowledge. And you could say that you don't want this from your theory, and that's fair enough, but I do. Okay. And then the way it will instantiate each physical theory is that a physical theory is fed as common knowledge within a logical system. In the same way that if all the agents went to play a game or to make some gambling, the rules of the gambling would be common knowledge to everyone. So in this way, the rules of quantum physics, for example, will be fed as common knowledge. On the other hand, as I said before, we want to associate the agents with physical memories, and this should be undergoing some kind of physical evolution. So we'll describe them as we'll need to be able to describe measurements from the perspective of both the observer and other agents. And we'll come up with some kind of minimal conditions for this that then we can apply to each theory. Okay, so what's this model logic? So behind the scenes, there'll be something called a Kripke structure. If you don't know what it is, don't worry about this, or you can read in our paper. Here, I'll just give you the element. Okay, but so I'll give you some elements, and this structure is what keeps them together. So we associate some agent AI with some knowledge operator. Okay, it's just some operator that you can read it as AI knows whatever is going to come in front. I'll give some examples later. Then, so you have one for each agent. Then you'll have some propositions. So these are just things that agents may know or reason about. Okay, so for example, the sky is blue, or it's raining, or the spin is up. Then there'll be some operators, and these are normal things like operator and, or, something implies, there exists something, for all, blah, blah, blah. Okay. And then behind the scenes, there'll be possible states in which these propositions that can be combined with model operators may be true or not, or may be true for one agent or not, or an agent may believe in or not. And then we'll have some set of rules to operate and combine these statements. So before I define this a bit more formally, let's just see some examples of things you'd like to model. So an example from cryptography would be this. So Alice knows that Bob knows that Eve does not know the secret key. And Alice also knows that the secret key is 1. Okay? So the way this is described in model logic is like this. So A means Alice knows, and then everything that's inside. Okay, so she knows that Bob knows. That is not true that Eve knows the key. Okay, so this is the negation operator. So Bob knows that Eve does not know the key. And Alice also knows, and that key equals 1. Okay. But then there's more things we might want to model, like a notion of trust between agents. So if Alice knows that Bob knows that Eve does not know the key, and in addition, Alice trusts Bob. Okay? So therefore, we should be able to compress this statement and say, well, therefore, Alice knows that Eve does not know the key. Okay? And we'll express this via some kind of trust relation. So this means Bob is trusted by Alice. And what this means is that if Alice knows that Bob knows something, that Alice knows this something. Okay? And this is similar to the consistency assumption in the Fabrica-Renner paper. Okay? And it's weaker than saying that, well, if Alice knows that some agent knows something, then this is universally true, which is the way classical epistemic logic is designed. Okay. But then I should also be able to make some inferences, like, oh, I know that Eve does not know the key, and I know that you need to know the key in order to recover the message, so I can conclude that Eve does not know the message. Okay? You should be able to combine statements like this. Okay. So that's expressed here, and this is the idea of making some inferences. So I know this thing, and I know that, well, in order to know something else, I'd have to know that, therefore I know that Eve does not know the secret message. Okay, so we want to be able to combine all these things. And this is all achieved given a very small set of rules for combining statements. So the first rule is deduction. Okay? So every agent, if she knows phi, and she knows that phi implies psi, then she knows psi. Okay? And later I'll comment a bit on this and whether this should come for free. The other one is introspection. So this is, if I know something, I know that I know this thing. And also, if I don't know something, I know that I don't know it. Okay. So I'm aware of what I know or not. It's not too necessary for our purposes, but it's. Is there a question? No.
There's a famous instance of someone talking about the known.
The known knowns and the
known unknowns
and the known unknowns. Yeah. So there's no unknown unknowns. I'm aware of the things I don't know.
Okay.
Yeah. Which you may rightfully complain it's too strong. But here it will not make a difference. So the other thing that we put is to replace something that existed in most like classical epistemic model logic, which was if some agent knows something, then this is true. Okay? And this was kind of he gave some meaning to what these operators was. Right, to what knowledge means as opposed to belief. But here we get rid of this and we just say some agents trust each other. And there can be this relation which says that, well, if J knows something and I know something, then he can forget the source of information. He can do this, what Adam called epistemic collapse. And then for whatever setting you have, you can set this trust structure as it feels reasonable. Okay, and we'll see that this leads to some problems. And then this idea of common knowledge, Adam also talked about this. So something is common knowledge if everybody knows that everybody knows that everybody knows that everybody knows it. Okay, no matter how many rounds you put there. And what we do is to put all the facts of your physical theory and experimental settings inside the common knowledge. Okay, everybody knows the Born rule. Everybody knows what happens when you apply a Pauli X gate, for example. Okay. So then this is one way to instantiate the theory. There could be further restrictions, which will turn out not to be important for our purpose of deriving these paradoxes, but in general, if you wanted to do this seriously of modeling agents, we should take them into account. The first one is complexity restrictions, and here I can recommend this essay by Scott Aronson, Why Philosophers Should Care About Computational Complexity. It's super nice. And the idea is, like, if you could do these inferences like without paying some price, then we instantly, rational agents know all of mathematics, for example. Right? And I mean, these are not the kind of agents that we want our theory to model. We want to model agents that are rational but not super powerful agents, right? So we could put some limitations or some costs for each reasoning step. Okay, or some cost on the memory size, or just some restriction like on, I don't know, polynomial number of steps of reasoning. However, when n is small, this doesn't matter, and here all these paradoxes can be derived with n very small, so with a very small number of deduction steps that you just need to assume that an agent can do them fast enough, like before the other step of the protocol is performed by someone else. So the other thing is, like, for now we just said some setting might have some trust structure between agents, and this should be generous enough to allow us to derive the usual classical reasoning to solve logic inference puzzles, but restricted enough to avoid contradictions, as we'll find later on. And so far, like, we've tried quite hard, and so far we don't have any good rule for which trust structures should be allowed. And this could be things like, oh, if I'm going to be measured in the future, then I shouldn't build any trust chain that goes past this point in the future, for example. But we haven't found any good way to settle this. Okay. And as I said, this already replaces the idea that knowledge is objective, and if an agent knows something, it must be true for everyone. Oh. And just a comment on what Rudiger said last time, free will, I think, can be incorporated into this kind of structures. So free will always be a relative concept. So I have free will relative to some causal structure, or I have free will relative to the other agents, for example. And this can be instantiated, for example, as a set of propositions that I know but no one else knows. And this could be a proposition about what I will do in 5 seconds. And no one else knows this, therefore I have free will relative to them. And with this, I think we can handle it. The other thing is that the idea of agents over time, like, am I in 10 years the same person that I am now? Is it fair to consider me the same agent? Like, if something is going to happen to my memory in the meantime, especially if someone is going to perform measurements on my memory, is this still a fair thing to consider? And this can handle this. So you can think of that you have many agents. So Alice at time 1, Alice at time 2, Alice at time 3. And then to say that, oh, there's some kind of continuity between them, or Alice at time 2 remembers Alice at time 1, for example, so they share some memory. You just use trust relations, okay, between them, and say that, well, they all trust each other, but in this direction. Okay. By the way, trust is not transitive. Maybe it's not obvious, but just because I trust Chris and Chris trusts Matt doesn't mean that I trust Matt directly. So I only believe things that Matt says if they come to me via Chris, which
through the filter.
Yes.
Through the filter of Chris.
Yes, it's like you're the
That's really implausible.
reputable. Yeah, it was not the best example, was it? Okay. Right. So this is relatively uncontroversial. Whoop. I guess. So now comes the part where we need to model the agents as physical systems. And first we need to define what a system is, and I don't want to put too much structure here. So we have something in the paper, but for now, I just say, well, it's something that can be an object of study of agents. Behind the scenes, this is characterized by a set of possible states, and then each physical theory can say what a system is. Okay, so in quantum theory, you could say, you could associate it with Hilbert spaces, for example. So now we want each agent to be associated with a knowledge operator as before, and now some physical system that's like their memory. And also kind of the free will, so the ability to perform studies, so for example, making measurements or performing transformations in any system that could be in principle other agents' memories as well. Okay, so now comes the tricky part, which is what's a measurement? And so I want you to criticize me, okay? So measurements, we say, is a type of study that agents can make, okay? And let's say the setting where Alice is measuring some system S, okay? And Bob is witnessing this. And by witnessing, he knows that Alice is doing the measurement. He knows which measurement, but she hasn't told him the outcome yet, okay? And he knows that this measurement has some outcomes labeled X, okay? So now I say that the measurement is characterized by a set of propositions, phi X, where phi X could be, I know that the spin is now in state up after the measurement, for example. Or I know that I obtained this. Satisfying the following. So Bob knows that there exists one of these x's such that Alice knows phi x. Okay? So he knows that Alice got an outcome. But he also knows, okay, that if he learns which outcome she learned, he knows that she could not know that it's not phi x. So this is the notion of having the experience of a single outcome. Okay?
What, can you say that one again?
So,
I don't understand that one.
okay. Bob knows that Alice got this outcome, so she can make this proposition, like the spin is up. Therefore, Bob knows that Alice cannot make the proposition the spin is not up. Yeah, or Alice cannot know this.
Should one of the knots be before K? Or?
Should one of the nodes be what?
The knots cancel and then it's a trivial state.
Oh, yeah, okay. Fine. Okay, here you could put any of the other outcomes, for example, then. Look.
So you're saying it's not phi y for any phi not x?
Yes, yes. Maybe that's a smarter way to write it, yes, rather than just cancelled.
So,
Yes,
so what
I-
is it that Alice knows? Alice knows it's not phi y for any y,
yes,
not,
yes,
not
exactly.
equal to x.
Yes, right. And if you get to a situation where you have this, that Alice knows phi x and Alice knows phi y, this is where we got the contradiction, because this is incompatible with our notion of measurement. So if in the end we have this thing that Wigner knows, that Alice knows that he got fail, but he also got okay, then this should be the contradiction with the notion of measurement as it is.
Wait, so why is this?
Go ahead.
Yeah.
Why is this still not a trivial statement? Because
But-
the set of possible outcomes is known.
Right, right. So put here, instead of known phi x, put here phi y. This is really the thing that tells you that they're incompatible. Yeah?
And you would say in a single world this is always satisfied? This assumption? If
Yeah.
you have a single world, you would, is this true, what I'm saying?
This is what I would say, but the
Yes,
fact that
no,
you're
no.
asking me is making
No,
me very suspicious.
now I want I want to ask you then the opposite. Then I would say, okay, this can be maybe relaxed in some many worlds interpretation.
Right.
And then I would ask, why would you then call this the same agent?
Right,
Hey.
then this is one of the ways out, is to then not call the same agent to the agents in a different.
But then it's not
branches.
about this.
But he's the same agent, right?
He's the same agent, but then it's a kind of trivial state. I mean, the only non-trivial statement is when you ask the question, well, if they are the same agents. So I don't see the necessity of this assumption.
So,
Because in single world, it's always satisfied, and in many worlds, it's just the whole kind of structure is then shaking because
yes, It's just to define what we mean by a measurement. And this is having like outcomes are incompatible. So if an agent knows one, it does not know the other.
Is it a way of saying that the outcomes are mutually exclusive?
Yes,
You
it's a way
only
of saying
you only
this.
arrive at one outcome.
You only arrive at an outcome.
Not
Yes.
some overlapping regions.
And if you don't have this property, maybe there are things in your theory that don't have this property and should still be allowed. But if I call it a measurement, then I don't want this. And that's how we get paradoxes.
Just a quick last question on this.
Yep.
Do you mean to say in that last bit after the arrow that Bob knows that A knows that it's not Y?
Yeah.
Or that Bob knows that it's not the case that A knows that it's Y?
I think that follows. That's implied by this, but it's not.
Well, saying that A knows that it's not Y is
Weaker than saying
you're
that.
saying that not
Yeah.
A knows that it's Y.
Yeah. Well,
I mean, I can know that it's not Y, but it doesn't mean that. Well, anyway.
and maybe they don't imply each other even. But the idea here is that Alice knows what she saw, right? So you don't want to have a negation before Alice. Yeah, we'll try to clarify this. Okay, so this was the simple part. So for the physical perspective of the measurement, I need to go through the quantum example to try to convince you, and then I'll try to do a more general way of seeing it. Okay, so again, now we want the measurement to also have some kind of physical thing representation. Yes. Yes.
Processing it, but does this imply really that there's kind of a hidden, I mean, in conventional language or so, a hidden variable there that stands for the outcome? Because the first condition somehow says there is a value which is maybe not unique, and the second condition also says it's unique. So I can really assign a value to it. I don't know it, so it's hidden. And
I wanted to keep this not so technical, so I hid like here timestamps. So, but this is after. So here you can have that Bob knows before the measurement that after the measurement Alice will know the outcome. Okay. And now this is all after the measurement. So Bob knows that after the measurement Alice got this, so she didn't get the other one. So it doesn't say that before the measurement there was a hidden variable determining what the thing would be.
yes, okay,
Right.
so you're saying it's more subtle because you have timings and,
Yes,
and
yes.
the statements change depending on the
Yes.
time.
Yes. And yeah. Yeah. Okay. So now again, how we model a measurement can be modeled different by different agents. And so I'll give you the quantum example first. Okay. So here's Alice's view. Alice is performing the measurement. Okay, and she's measuring this qubit here that's in substate phi s, and that's where she stores the outcome of the measurement. Okay. So in her perspective, she just did a projective measurement in the z basis, and then she got a classical bit here, and condition on this classical bit, she flipped this qubit. Okay. So if it was a 0, she stored a 0 state here, and if it was a 1, she stored a 1 state. She can still believe that she has a quantum memory, that her memory is a quantum system, but she just puts this classical thing here. So from someone that's completely outside, so in this case it will be Ursula, and I'll explain why. This is because Ursula Le Guin has just died by the time we wrote this paper, so he added her to the paper. Anyway, so from her perspective, well, we have this old story of when Alice is making a measurement, there's a pointer that she brings into interaction with it, and then the pointer goes to superposition to being in the left and in the right, and then photons hit the photon, hit her eyes, it hits the pointer, hit her eyes, etc. In the end, she's like in this big superposition, which Ursula can reduce to just a C0. Okay, and that's the physical evolution from Ursula's perspective. So if she had measured an X from Alice's, maybe she doesn't even need to think about how she implements it. She just says it's an X measurement. But from Ursula's perspective, it's like, oh, she did a Hadamard, and then she performed the C0. Okay. So from Ursula's perspective, all she did was entangle these two systems. Okay, there's no like fixed outcome here, and this will be important later when you talk about box world. Okay. Up. And now bear with me with what I mean by the following, that with this physical model for Alice's measurement, it's information preserving in the following sense that suppose that Ursula wanted to go and measure this qubit S before Alice made her measurement. She wanted to measure it in some arbitrary basis, X or Y or Z, whatnot. But now Alice already arrived and she performed this operation, right? So, but Ursula can still do a joint measurement, a joint operation on S and her memory A that yields the same results as if Alice had not measured S in the first place. So, so for example, if Ursula wants to measure X, all she needs to do is now perform this joint operation, which is a C0 on S and A, and then perform this X here, okay? Which is the same as measuring the whole thing in the basis OK fail of Renato. So yes, 0, 0 plus 1, 1. Yeah, you believe me in this? So whatever Alice measured here, there's something, whatever Ursula wants to do, there's something that she can do that kind of, in this sense, it undoes Alice's measurement, but that's not what matters. What matters is that the statistics she gets and all the conclusions she can draw from this are the same as if she had measured this directly before Alice had arrived. Okay. So what this does is to replace the counterfactuals of measurements, so I could measure X or Z, with just measurements that are actually performed but by different agents. Okay, so so Alice goes and measures Z, and then Ursula goes and measures X. And this is what, we'll talk about this later, is one of the sources of these paradoxes and contradictions. Okay. So here's the example again. And now here is a bit more formal for the general case. So Alice measured S. She performed this measurement M, AS, okay, witnessed by someone else, Bob. But the memory update, as seen from Ursula's perspective, is just some transformation on the state of the system. And what the state of the system is depends on the physical theory of a joint system of S and the memory of A. And it's information preserving from Ursula's perspective. If for anything that Ursula wanted to have performed on S, if Alice had not gotten there first, there's a new study that she can do on the joint system of S and MA that yields the same results as the original one would have. Okay? By some results, so if you think of quantum theory, you can say it should have the same statistics, but more generally just say for any proposition that Ursula can do now after this measurement should be able to reproduce any proposition she should have done if she had measured S directly. Okay. We will, when you see the examples, it will be more concrete. Okay. So this is all we need, I think. Yes. Oh. Yeah. This is all we need for now. Are there questions up to now? Okay. This is not the same as saying that Alice's measurement must be a reversible transformation or anything. And we'll see a counterexample. So here's Nuria on a tree. And now we're going to see quantum theory, and this will be very, very fast because we've done nothing else this weekend. Okay, so how do we instantiate the conditions? So the memories now are some qubits. We have the von Neumann model for measurements, which is what we saw before, this unitary implementation, which we already saw as information preserving. And there could be other physical implementations, like, for example, a collapse theory that is not information preserving, in the sense that if Alice collapses a state, there's nothing Ursula can do that would retrieve the original statistics. Okay, and everything like Born rule, quantum gates, experimental setting, etc., is fed as common knowledge. And we could think of more sophisticated agents like the quantum, having their own quantum processes, or seeing the whole reasoning process as a unitary evolution. And this we do in this new work with Simon Mathis that Renato talked about. Okay, but for now we don't need this. So, Farriger-Renner thought experiment here, because you've seen it so many times this weekend. I'll just show you the little animation that Nuria made, so it will be very quick. Just have in mind that in order to derive the contradiction, the trust structure that we need is this: is kind of Alice is trusted by Bob, which is trusted by Ursula, which is trusted by Wigner, and I'll tell you who these people are. Okay, so Alice is kind of the friend in the first box. She has the system in this state. It's a qubit, and her own memory is in state 0. Okay, you ready? So it comes, she measures it. So from the outside, she's just getting entangled. Now she prepares a system depending on the outcome. Okay, she prepares one or the other, and she gives it to Bob. Oh, she's now entangled with this. Gives it to Bob, and Bob measures it as well. Now they have this whole big entangled state. That's like a Hardy state with double number of qubits. And now Ursula and Wigner are the people who measure them in this special basis. And now they make all these statements, right? Alice knows that if she got 1, Wigner will get a fail. Bob knows if you got 1, Alice got 1. Ursula knows that if she got OK, Bob got 1. And Wigner knows that he got these 2 outcomes. OK. So take all these statements. We can combine them using all these model operators, which you do in the paper, but I will not subject you to this. And you get this paradox that Wigner knows that he got OK and that he also got fail. Okay. All right. I will not go into detail because I assume you're all familiar with this by now. But in this model logic paper, we do every step using model logic and define this contradiction. OK. And here's an easier way to look at it, which is just a circuit. OK, so here are the 2 systems they have. We call it PR because later we'll have PR boxes. Doesn't matter. So Alice measures this system that's in this funny superposition. Then depending on the outcome, she performs a Hadamard here on the system that she gives to Bob. Bob measures it. It is all seen from the outside, so from Ursula and Wigner's perspective. And then Ursula does an X measurement here, and Bob does the X measurement there. That's the OK fail basis. So, yes?
It's really cool animation. I haven't seen that before, but the animation also has a reasoning process in it. And
Sorry?
because, you explicitly said it's part, or in the animation, they do this reasoning.
Yes.
Shouldn't this reasoning also be reflected by this circuit?
So I'll
Or is it?
no, then it should be a very long circuit. I mean, of course we want. I mean, of course this is what we do, and this is what we're doing in the new paper. But this will be a massive
Someone can
circle.
just think of it as an abstraction of
This
that.
is just an abstraction of
Okay.
just thinking what's happening with the memories.
Okay.
Okay. And you can think of this as like a logical 0 and logical A that already includes all the reasoning inside.
Yes. Okay.
Okay. Yes. Okay, so one way to look at this that I started to like is to look at this. So take this idea of what this model of measurements allows us to do is to replace this counterfactuals with measurements performed by different agents. It's okay? Okay. And then we can look at just Hardy's paradox, okay, where we have the first, where we have this initial state and then we post-select on minus. And what we have here is like the Abransky and all version of looking at contextuality where, so maybe I can write. So here's Alice's measurement with the 2 possible outcomes. Sorry, this is Ursula's measurement and the 2 possible outcomes, plus and minus. This is Bob's measurement and the 2 possible outcomes, Alice's and Wigner. Okay. Now, and this is where we start. So we start by saying, well, we post-selection and they're getting minus, minus. And then you do the reasoning like this. So if Ursula got minus, then she knows that Bob got 1. If Bob got 1, he knows that Alice got 1. If Alice got 1, she knows that she predicts that Wigner will get plus, and hence you get the contradiction. Okay. And this picture is just, if you can remember the paradox and you can relate it to this picture, then it will be easier to explain the box world paradox. Okay. Okay. And whereas here we're just talking about counterfactual, so alternative measurements that could be done in a 2-qubit state, okay, where we measure the first qubit or the second qubit, and these lines are connected. Essentially, they're going to be connected if there's a trust relation. So if you can do the two measurements in a compatible way. Okay, so that's me on a tree. The colors are not quite right. So now let's see what we do in box world.
Hey, at least you got color.
Sure. Okay, so very quickly, So generalized probability theories are this framework where the objects are boxes that are characterized by just some input and output behavior. Okay, so we put in some inputs, you can get some outputs, and then they're characterized by state vectors that just give you the probabilities of outputs given inputs. Okay, so something like this: probability of getting output A given that input was 0, for example. Yep. And what's important to note is that these are not physical theories because these boxes do not correspond to systems. They're just a single-use function. It doesn't tell you what happens to the box after, and you cannot look inside, and it doesn't have any dynamics theory. Okay. But there's many different theories that are determined by what allowed state vectors are used, and this is used to study non-locality, for example. So box world is a special case, so that is maximally non-signaling boxes. So, oh, beautiful. So essentially, it's a GPT that allows for PR boxes. So PR boxes are, as most of you know, they are boxes with 2 inputs, and you give one to Alice and one to Bob, and 2 outputs, such that the outputs are non-signaling on the inputs, but they satisfy this condition, which is the CHS edge condition. Okay. Good. In this world, the allowed operations are just wirings of boxes and pre- and post-processing of outcomes and of inputs. Okay, so you're really not allowed to go and change the box. And this is the world in which we'll work. So let's recap. So we'll see that Alice does a measurement, and now how does Ursula see this? So this is the system that Alice measured, represented by this box, which is not a physical system, but yeah. So from Ursula's perspective, from Alice's perspective, she's going to run this box. She can only run once, then the box disappears. And then based on this, she'll prepare a second box that's her memory, which could be, for example, just a bit, which says 0 or 1, depending on the outcome. Okay? But from Ursula's perspective, this is not what happens. What happens will be some kind of the equivalent of the C0, but a bit different. So from Ursula's perspective, Alice did not run the boxes, but instead she just prepared a new box for her. Okay? And she prepared it at time 1, at the beginning of the experiment. Then later on in the experiment, Ursula will run this box.
So
yes?
this is the thing that confuses me. Are you sure that Ursula's box exists in this case?
Well, it will exist later. Maybe I can give. Ask me this again after I give the example, maybe. Yeah. In the same way that in quantum theory, from Ursula's perspective, Alice did not measure anything. She just prepared this new state that was a C0 of the 2 original systems. Here we don't have systems.
Well, we do.
Okay, so we have a problem, which is that all reversible dynamics in box world are trivial. And by trivial, I mean we can only relabel outcomes or permute systems. So we'd have 2 options. Either we make it reversible and trivial, which does not sound too promising, or we make it non-trivial and irreversible. So we chose this one. And what's fun is that a transformation can be irreversible in the sense that you cannot run it backwards, but it can still be an information-preserving measurement in the sense that we saw before. That Ursula can run her new box and get the same statistics as if she had run the small box originally. So from Ursula's perspective, first she thought that Alice had access to 2 boxes, right? One which was like any bit, any G bit, so any 2 input to output system with some probabilities P and Q for the 2 distributions. And maybe she had access to some other system that was her memory, okay, that was initially initiated, that will be destroyed, and she'll build something else, okay? And then the kind of things that are allowed in this case will be that Alice prepares a system with 2 inputs and 2 outputs that behaves like this. So here you have like P001 minus P, and here Q001 minus Q, where P and Q are the probabilities from here. And in the middle, it can be anything. So this will not be reversible, and we check that it's an allowed operation. Okay. And here's a very simple example of such a thing. This would be if Alice's preparation would be just take a memory, run it, from the perspective of Ursula, and then just make it trivial such that it always outputs 0. Run this, prepare this box to be ran, and then just C0 the outputs, okay? But she has not actually run this box yet. She just gives this new box to Ursula such that what Ursula can do is she puts some inputs here and here. Here nothing happens. She just gets a 0 here, and then she'll get something there. And here this input will be transmitted, so on. Okay. It's a very trivial thing. And unlike the quantum case, we don't have a story because we don't have dynamics of. We don't have a dynamical theory for box world, right? You could come up with other ways, okay? And then we tried to come up with other ways that's far more complicated, but for like no good reason. So like, if you criticize this, which is very fair, then please propose some alternative or tell me why we cannot come up with anything. Okay, so if Ursula wanted to do now this measurement that she'd want the same statistics as if she'd done X, so what's in red is what Ursula does, okay? She just needs to, at the end, undo this C0, this classical C0, and she'll get a big box that she gets where she inputs X, the output is A, and the probabilities are given precisely by the probabilities of the original box. Okay? So it's really, from Ursula's perspective, Alice did nothing but to wire the systems in this trivial way. But of course, from Alice's perspective, something else happened.
I'm not quite sure why you call this irreversible. Because, I mean, if you're assuming that Alice is not actually putting inputs into the boxes, like what you've drawn in, I mean, all you've basically done is a C0, which is a reversible gate. Right? So in what sense is it irreversible?
I think it's irreversible in the sense that I put something here and I run this box, but I'm not. I had a good answer to you this morning, but now I don't anymore. So, yeah, if you look at the map that implements this, the matrix that implements this, the inverse map is not an allowed operation, but I also don't understand why. So it could be that it is, but this is not just a relabeling of the system or a permutation, right? So by Gross and friends, it should be not reversible. Okay, so now let's look for the paradox, or paradox, as Ravi helpfully told us. It's a paradox because it's a pure box paradox. Okay, so this diagram, again, now these are not boxes, it's just a way to tell you what's happening in time. Okay. So in time, what's happening is that Alice and Bob share a PR box, and now Alice comes and measures her half with some her half is this P with some input XA, which could be 0, for example. She stores the outcome in MA. From Ursula's perspective, this is seen as this operation that we saw before. Okay. Then Bob measures his half, okay, 0, stores his outcome. And at this point, Bob can reason about what Alice got. Then Ursula measures this whole system with the other input, okay, just needs to be different from this. And Wigner then measures this with the other input. Okay. And in the end, this will work whatever outputs they choose here, as long as they're different. Whatever inputs they choose, as long as they're different. And it will also work for whatever outputs they get. Right. If I actually wanted to draw the diagram of what's happening, I would have to draw these things for this step and for this step. Okay, so this is just in time. To see that you get the paradox, again, we look at this relation to the counterfactuals. Okay, so here we have this rule for the PR box correlations, and then we can think. So Wigner, say he measured 1. Suppose he obtained output 1. Then what does he know about Ursula's output? Well, because she also measured 1, and the correlations must satisfy this. So A plus B must be X times Y, which is 1 times 1, so that's 1. So he knows that if he got 1, then Ursula must have gotten 0. Okay. Then Ursula can think about what Bob got. Okay. And again, because you have the same trust relation, she can do this. So again, the PR box condition for correlations tells us that their outputs must be the same. So Bob got 0. Bob can think about what Alice got, and again 0. And then Alice can think again, because she sees now Bob's measurement as a unitary evolution, she can think about what Wigner will get. And because of the PR box things correlation, she concludes that he'll get a 0. Okay. And if we had started with the output that Wigner measures 0, actually, instead of 1, you'd go around and you get the contradiction. If you change the inputs that they measure, you'd still get a contradiction. Okay. And then you can express all of this in model logic in the same way as before. So it's a bit of a stronger contradiction. And Samson and friends, they have a name for this, like strong contextuality with or logic versus whatnot. But the idea is that in box world, so we always get a contradiction independently of the choice of measurements or outcomes that they get. Okay, so this tells us that maybe this kind of paradox is not unique to quantum theory, but we need something from the theory, and the question is what. So conclusion is this is Villassini playing what used to be a tree. So here's the current conjecture is that if you have a physical theory where you can have this kind of information preserving measurements that allow you to replace counterfactuals with factuals, and you have some kind of contextuality, then this leads to multi-agent paradoxes. Okay. So this is something we'd like to prove. And so some non-contextual models will not be able to find them. So for example, in Spekken's toy theory. The other thing is to create this software that Renato talked about that we're doing with Simon and Nuria to instantiate different theories and all the protocols and all the reasoning so that I could say, oh, feed me box worlds and a collapse theory, or feed me, I don't know, unitary quantum theory and they believe in this interpretation, or change the protocol by a little bit and it should tell you if there's a contradiction or not. The other thing that I already mentioned before is these conditions for what trust relation should be allowed or not, because you could claim that maybe it's unreasonable that these agents are allowed to trust each other in this way. And then, I mean, as a last resource, maybe what we can try to do is kind of weaken this idea of the cryptid structure, or change the scope of what an agent is, or think about how this applies to many worlds kind of interpretations, and try to see if there's a different logic system in which to base things. Okay, so that's most of it, except now I will plug our upcoming summer school. So where's the squid? Oh, there it was. Oh no. Okay. Come. So this is a summer school that will take place in Zurich, 17th, 21st of June. Master students, PhD students, early stage postdocs are very welcome to come. The registration will open soon, and let me just run you through the program. So we have the first day for basics. So Valerio will talk about non-locality, device-independent things, and Tom Galli will talk about GPTs and deriving the Born rule from principles. Then we have a Bristol day, or a time and pre and post selection day, with talks by Tony Short, Ralph Silva, and Sandro Pesco. Then we have a day for causality. So first Miriam will talk about this DAGs and how to work out if causal structures are classical or quantum or post-quantum. And then Villassini will talk about applications and different approaches to this, like process matrices or causal boxes or whatnot. Then we have a math day, where Matt will talk about interpretations of quantum theories, so very much like the talk he gave yesterday, but 3 hours of this, so it will be great. And Matt will talk about contextuality. And then we have a day for essentially try to derive physical theories from just observers and their memories. So first Marcus will give his hamster talk, as most of you might know by now, about deriving physics from information theory, and Paolo will talk about this deriving special relativity from cellular automata. Okay, and the squid on the block sphere is kind of a new association that Nuria and I created to organize summer schools, and we're always looking for lecturers for this kind of things. And if you want us to organize summer school in your university. There's nobody like us. We're amazing. All right, and that's all I'm going to say.
That still didn't explain the choice of a squid.
Right, we went through months of agonizing about this, and then
You tried a dog first. Dog didn't work on the blocks.
no, SQUID stands for we have some nonsense like Schools for Quantum Information
I
Development.
thought maybe it stood for an actual squid, like the squid states.
And they can stand for this too. And then Nuria drew this, and then there's no
School for
coming back.
Quantum Information. Schools for Quantum Information Development.
Yeah.
Schools for quantum inquisitive doctoral students.
It's even better. Yes.
I was going to drop dumbass. Schools for quantum inquisitive dumbasses.
I have a real.
Okay.
We're still not sold on this PR box stuff. So I'll tell you why. So in quantum mechanics, if Alice makes a measurement, say in the 0-1 basis, and Wigner is outside describing that, then Wigner Alice thinks she's made a measurement. Wigner describes it as a state in which the 0 basis states are correlated to her measurement states.
Mm-hmm.
And now Wigner can do a measurement that is equivalent to having done an X measurement before the thing. But that doesn't change the fact that prior to doing that, Alice has done a 0 versus 1 measurement. But it seems like this is not the case here, right? So what happens is you have this thing which correlates your PR box to the memory.
Mm-hmm.
If Alice puts in a Z, it correlates with the Z measurement. But if we just view the whole thing as a great big box and Ursula comes in and puts an X, then we never get into a situation where Alice is correlating with the Z measurement. She never has that information. So it seems like this is quite disanalogous to what's going on in quantum theory, and it seems like so in some sense, because you have this irreversibility, the only way of getting Alice correlated with the Z measurement is to put in a Z, and if you demand that, then you don't have this information preserving.
Right, but what you have here is that, okay, I agree with this, and this is a problem. Okay, but I mean, I agree that
you agree with him.
I leave this open to interpretation. So, but what you have is that in the quantum case, Ursula knows the correlations between Alice and the things. And here it's just not accessible to Ursula what this was, because she modeled this in a completely different way. But Alice has a different way of modeling what happened, which is she actually measured one or measured the other.
In quantum theory?
No, in box world. So I didn't write here what.
You can't put in both an X and a Z into the box, right? If
No. But in the same way that Alice in quantum theory, she made one measurement, not both of them.
Right, exactly. But the thing is, in quantum theory, Alice getting correlated in the Z basis doesn't preclude somebody from measuring the X basis on the joint state later. And here it seems like if Alice gets correlated in the Z basis, it will only happen if she actually puts in Z as the input to the box. So you can't then have somebody else who puts in the X input to the box, because that means that Alice never did that measurement.
But from Ursula's perspective, Alice never did any measurement, right?
Well, there has to be some sense in which Ursula's description says that she is doing a measurement. Otherwise, what license does? I mean, how can you?
Well, the thing is that
if Ursula doesn't think any measurement has happened, then there's no license for getting any kind of paradox, because you need to have a situation in which Ursula thinks Alice has made a measurement and got a definite outcome.
No.
Basis.
No, you just need Ursula to believe that Bob made a measurement, and you just need Bob to believe that Alice made a measurement. That's what the trust. So.
Yeah, but the physical description, in the physical description, it should be that Ursula has some license for seeing that Alice has made it.
All right. I mean, you could have another box here coming with an output that says I made a measurement. And it doesn't change.
Well, you know how I feel about this, lots of arguments, but it seems like that in the physical state that Ursula assigns prior to, I know you said there aren't any states in this theory, which I disagree with, but prior to her putting the X in the physical state that she's assigning to Alice's memory in the box, there is no correlation in the degree of freedom that Alice is supposed to think that she's measuring. So what license does Ursula have for saying that she thinks that Alice has made a measurement? It seems to me that in that description she hasn't, and actually Alice never can make the measurement because putting the X into the box precludes her from putting the Z into the box.
Would you make you happier if Ursula's description of the measurement had here, like that Alice adds her own choice of input to Ursula's? So here you'd have, so if Ursula Lidia puts this X, what comes here is like X of Ursula plus X of Alice. And then it would be more of a signature that Alice did something?
If they both put in X, if X goes into the box, whoever's the one who's putting it in, then simply the Z measurement is never made, according to anybody, right? We need to convert the counterfactual alternatives into an actual sequence of non-counterfactual things to get the paradox, right?
Right, but you don't need to have a consistent global physical picture. You just need to have them like 2x2 pictures.
But you do need Ursula to think that Alice did make a measurement of Z. Because if Ursula doesn't think Alice made a measurement of Z, then what is she basing her conclusions about Alice's measurement of Z?
Right, so again, I put here another box saying that gets input 0 and the output is just what Alice's choice of measurement was.
But Ursula's overriding Alice's choice of measurement by her input.
Yes, but then she also gets information about what Alice's original measurement was.
Well, I can see we're going to have to agree to disagree.
But I just... Yes, so I mean, what's your solution? To say that
well, I don't think you can do this paradox in...
But can we model memory update at all?
In box world?
Yes.
No. I mean, this is to me this is one of the deficiencies of box world. If you can't do things, if you can't implement a measurement interaction reversibly, then there's a lot of things that we do in quantum theory that you just can't get off the ground, and it's one of the reasons why it's not a reasonable physical theory.
Right. Okay.
That would be my attitude to it. That you just can't do this.
Right. So here what I do is that there is some signal, some signature that Alice performs some measurement, and this is by giving a box that has a different behavior than the original box that had. But of course, it does not satisfy all the properties of that quantum measurements do. It does satisfy enough that we can get around with like applying our logic and still getting.
Yeah, of course you can, but it's like the question is like, is it justified to apply that logic there? I mean, I would say the justification for Wigner saying that Alice made a 0-1 measurement in quantum theory is that Wigner writes down a state in which there's correlations between the memory and the 0-1 basis, and that's why Wigner is justified in saying Alice has made a measurement in the 0-1 basis, and that just simply doesn't happen here. So I don't see what.
Yes, fair enough.
I mean, so I think if Ursula does this, then simply the idea that she trusts Alice's statement that she made a Z measurement is simply just must be.
But
false.
she does not. That's the whole point. That Ursula does not need to trust Alice. She just needs to trust Bob, right?
Okay, but still.
The chain of reasoning goes like this, right? She just needs to know that Alice performs an evolution.
But the same thing still applies for Bob, right?
Yeah, but she models Bob as making a measurement where he got the output and then they prepared a new box called the memory that is correlated with this output, which is not. So she does not model Bob's measurement like this. Okay, because she knows that he got an output. In the same way that in the quantum case, Ursula does not model Bob's measurement as the C0, she models it as like, okay, we had this state, and now Bob does a projective measurement. And Bob models Alice's measurement again like this collapse thing. That's what the trust means, that he trusts that she made a measurement. But you don't need to have it here. And you don't need to have it there.
Somebody's measuring it. Somebody's... so it's the case that Ursula models Alice as a C0 and Vigna models Bob as a C0, right?
Yep. Yes. But Ursula models Bob as having actually performed the measurement and got an outcome. Yes.
It's kind of related, but can I just try a different tack? Like forget about box world. Just imagine quantum theory that had real collapse, like a GRW collapse model. Wouldn't you still be able to do this thing of like having the measurement box and putting a C0 and then setting up the whole paradox? Whereas we would assume that if you have a collapse model, then you don't have these paradoxes.
No, I don't
Doing
think
the
so.
time
I don't
in the
think so.
columns.
No.
Like, cause you could form. Think of your collapse model as just an operational theory where you have boxes that.
Okay,
where
depends
you
on
choose
who's
which
modeling
measurement.
collapse, right? If again, I mean, to derive the original paradox.
Well, just do it exactly as you said. That each person.
Yeah, but this is what we do to derive the paradox. So again, Ursula models Alice as this unitary thing, but she models Bob as a collapse. Okay, in the sense that she can think about the outputs that Bob got. And Bob can model Alice as a collapse, and Alice can model Vigna as a collapse. But Ursula models Alice as unitary, and Vigna models Bob as unitary.
Right, so what I'm asking is, why does Ursula need to model? You're almost giving an argument that it doesn't matter how Ursula models Alice and how Vigna models Bob. In which case, it doesn't matter whether or not you have a collapse.
They just need to know that it can perform an operation that does whatever she did here.
Right, and so I'm suggesting that instead of undoing the unitary, they just do the same thing that you're doing here of overriding the choice of measurement.
Yep.
So then you would say that there is a paradox even in a GRW.
No. Because then, no.
Well, I'm not clear why you couldn't do this same thing.
I mean, it did.
Like, just think of GRW as a GPT.
It's about who models who as collapse and who models who as unitary. And for this paradox, you need this to model this whole evolution here as unitary.
But it wasn't unitary in the box.
No, but it was information preserving. In the sense that it could overwrite. Whereas if she had modeled like this as a collapse, then she could not go and do the X measurement and obtain this in statistics, right?
Right.
It's different.
But I'm saying instead of doing that, she models it with the override thing.
Yeah, but that's not the collapse theory.
But it's something you could physically do in a collapse theory. Like in a collapse theory, you still can measure qubits and decide what to measure and like all of that stuff, right? It only breaks down on larger scales. Anyway, I'm probably banging
Do you
about
want to
this.
postpone this discussion?
Yeah, you can.
Yeah, just last question by Chancellor.
Yeah, maybe I'm posing a similar question, but not so precise. This request that agents are agent and the system seems kind of very important, and for every probabilistic theory that should be universal, I would expect something like that.
Right.
So because I take these probabilities read out in some procedure, I still assume that this procedure can be again described as a state from somebody else, and it reminds quite to the purification assumption, which we know from Julia et al. Reconstruction, that it's with set of other axioms actually sufficient to uniquely define quantum theory. So I wonder how to avoid these situations that we are now thinking that it's also possible in a box world, that well, really, what are these elements that you might add in this request that every agent should be able to be described within the theory? Somehow theory is closed as a system to really get into the quantum theory. That would be a great project, I would say.
Yes, I don't know. I think this is weaker than, I mean,
Yeah, it's
definitely
weak.
weaker
It's
than
weak.
Just to comment on that, I mean, it doesn't imply a purification question, because what you need here is the purifiability of the dynamics, but not of the states.
Yeah.
So this is possible in classical theory, for instance, whereas the purification question. But I think it is a strong constraint on theories.
Okay. Do you want to thank Lidia again?
Oh, okay. Yeah, okay.